Perfect. One minute. Okay. Okay. Firstly, hi guys. This is NLP session 2 actually. Typo that one. So 1 minute. Yeah. So today we'll be okay. Yeah. Fine. So this is NLP session 2. Think we got a mistake on the title here. Today we'll be talking about Tf Idf vectorization, document similarity, and text summarization. So yeah, today's agenda is as follows. We'll be delving into Tf Idf vectorization and why we are doing it in the first place. We'll also be introducing you guys to computing similarity of documents, and we'll also extend this understanding of Tf Idf to text summarization. So yeah, the expectation and outcomes are same as the agenda. We want to explore Tf Idf and use that knowledge to summarize documents and find similarity between them. So a brief recap of previous session. Also, if you have any doubts, please unmute yourself or put it on the chat box. I have my fellow mentor Chakita here. Either her or I will answer. Moving on, a brief recap of previous session. We have so far been given a glimpse of what NLP is and what it has to offer. We even went on to learning the different aspects of pre-processing and finally saw the bag of words representation. Before I move on, do you want me to give you a much more detailed recap of previous session in case if you all didn't attend? Say yes or no in the chat box or unmute yourself. Okay. Okay. Thank you for that, Vishal. Fine. So yeah. So before I move on, I want you to think about this. This is based on what you saw and learned in the previous session. Is the bag of words form suitable for every NLP task? If you want, you could unmute yourself and speak about it, or you know, uh, type it out on the chat box. Anyone? You guys have any answers for this? Okay. Why do you think so, Justin? Any reason why? Uh, think on terms of how what it fails to capture for a given textual document. Correct. Perfect. Yeah. So that's like one of the drawbacks. So can you think of other methods that can overcome this? Think about today's title. That that's how we would be going about it. Anyway, um, so some of the problems associated with the bag of words representation is that the size of the vector increases with the size of the vocabulary. So thus sparsity continues to be a problem. So in order to avoid this, we need to control it by limiting the vocabulary to n number of the most frequent words. So what I mean by this is that let's say we had the bag of words model here uh, with n different documents and each of them having uh, m words. Okay, my handwriting's bad, but yeah. So according to what Chakita told last session, so the bag of words model basically it looks into where the frequency of the word in a particular document. So you'll either have, if it occurs twice, you'll have 2 here. If it doesn't occur, you'll have 0, 0, and so on. So what I mean by sparsity is that, let's say you have a really long document and you split it into various sentences and done this model. What basically happens is you'll have these occasional terms which have a number n associated with them, which is followed by a lot of zeros, for the simple reason that they're not there in that um, particular sentence. So what the problem this poses is that if we are doing any computation, obviously the size of this matrix increases. So to check if a word is there in a particular sentence, we need to iterate throughout the entire matrix, and this is computationally expensive. So this is what I mean by sparsity and how it hinders the features of the bag of words model. So yeah, moving on. So the second problem is that it does not capture the similarity between different words that mean the same thing. Suppose say we have 3 documents which says I run, I ran, and I ate. So for all these, the frequency is obviously 1 for the word run. Even for ran also it would be 1. But if you think about it, what message it conveys is different. So there's the tense which comes into picture, and the word form. So if we use this model to let's say evaluate a particular essay, we would get it totally wrong because it's based on the wrong assumptions. And the third problem is that this representation does not have any way to handle out of vocabulary words. What do I mean by this is that um, let's say we had this 1 minute, yeah, let's say we had this huge document corpus on which our model is trained on. So what, let's say it's the task of identifying the sentiment of a given text. So what I mean by sentiment is that he's a wonderful boy, so you get a positive sentiment for that. He is evil, obviously on the contrary it would be a negative sentiment. So let's say we have trained a model based on the bag of words representation to identify the sentiment of a particular statement. So let's say our model is trained to predict the line, the positive sentiment for the line, he's a wonderful boy. But let's say in the test scenario where, let's say, if you have deployed a model and the user enters this sentence, he's a nice guy. So what happens there is that the model won't be able to realize that nice and wonderful are synonyms. All it knows is that the frequency is 1 and we can't, yeah, so that's the drawback. It doesn't really handle out of vocabulary words. So yeah, another example here. Suppose we have statements like that is the only problem he could solve, and he was the only one able to solve that problem. So if you look at it, the I mean the bag of words representation would be identical, but the meaning which they convey is totally different. Yeah, and this is what I mean by sparsity. Anyway, well, what is the solution? The answer is Tf Idf. Well, it's sort of the solution because it overcomes some of the drawbacks of the bag of words model, but it really, okay, I won't talk about its limitations. I'll talk about what Tf Idf is first. So, understanding Tf Idf better. So what is Tf Idf? Okay, Tf Idf means term frequency inverse document frequency. So it's a way to score the importance of words or terms in a document based on how frequently they appear across multiple documents. So let's say we have our model has been trained on several different documents. Again, let's take the sentiment analysis task. So if there's a unique word which appears in several documents, it's important. So we give the word a high score. How we'll give the score, I'll come back to it later. So on the contrary, if a word appears in many documents, it's not a unique identifier. Give the word a low score. So a simple example would be like we have a lot of common words like the, for, and, but. So this appears in many documents, and this is not that important. I mean, it is important on a grammatical scale, but a big picture when it comes to NLP is that they're not that important. So what TF IDF does best is that it scales down these less important words and scales up these more important words. If you think about it, bag of words never had something like this. So this is what TF IDF does. Okay, so the math behind TF IDF. So yeah, it's divided into two segments: the term frequency and the inverse data frequency. And TF IDF has a whole. So the term frequency. What I mean by term frequency is, again, it's in simple words, the frequency of the term. Let's say I had statement like, um, you guys want to help me out with any statement or something? Feel free to mute yourself and talk. The Himalayan mountains is one of my dream destinations. So I hope you can see this. So term frequency, basically it how frequently the term appears in a particular document. So let's say we have like a lot of lines which follows this Himalayan mountains, like features about mountains. And so the term frequency basically refers to how frequently the word appears in that particular document. Mathematically, it's Nij by the summation of Nij. Basically, Nij is the number of times it occurs, and summation is the total number of words. So now, the differentiating factor here is the inverse document frequency. So it's the logarithmic function of n by dft. So 1 minute. So n here is the number of document. Again, we have, let's say we have a task where we have trained it on different documents. So n would be the number of documents. Let's say we had we have different articles based on mountains. So the number of articles would basically be n. And DFI is basically that one particular word, its frequency across all these documents. Okay. If you didn't understand what I meant by this, there's one example here. Think this would help you understand it better. So consider the two sentences. The car is driven on the road, and the truck is driven on the highway. So wait, before that, how do you think we would approach this? Like, what is that first step which is part of an NLP pipeline? Anyone wants to guess what it is? Anybody? Guys could type it in the chat box or mute yourself and speak. It has something to do with removing certain words.
Like removing the is, the, like words.
Correct. Stop words. What is that entire procedure called as? Stop words, stuff like removing this. Stemming, lemmatization. Correct. It's called pre-processing. Well, that's what we do here, but for the simplicity of explanation, I haven't done this here. So to give you an idea of how it's done, so this is the term frequency. The car, these are how we have divided into different tokens, these sentences. So it'll be the car, truck, is, all these different tokens. And the term frequency for the in the first sentence would be 1 by 7. So basically there are 7 tokens, 1, 2, 3, 4, 5, 6 and 7, and its frequency would be 1 by 7. And in the second statement, again 1 by 7, there are 7 tokens. So that's how we compute the term frequency. So now the interesting part is the inverse document frequency. So there are two documents here. I know the usual definition of document is like a series of sentences which is not as small as this, but for sake of simplicity, we'll consider this to be two documents. These two sentences are two separate documents. So n here would be the number of documents, which is 2, and dfi, which you saw here, would be the term the number of times the term the has occurred in both the documents. So again, that's 2. So log of 2 by 2, which is equal to log of 1, which is 0. So you might be wondering, okay, anyway, before I go across this, don't you think that if the TF IDF turns out to be 0, it's doing more harm than good? How do you think we can overcome this? Anybody? Anyone? See, like the entire idea of TF IDF, its essence is lost if if the product turns out to be 0. So is there like something which we could do, some adding of a particular term? Okay, okay, it's pretty simple, guys. In case if it does turn out to be 0, we add a +1 to it. That's all. It's as simple as that. So that's how TF IDF on the whole looks like. Um, Again, I want to throw this question around. So you guys now have a familiar understanding with what TF-IDF is. You guys, can you think of some limitations of TF-IDF? Anyone? Feel free to speak, guys, because like there is no correct answer for this. Like, if you come up with a limitation which we haven't heard of, it's it's like sharing knowledge with everyone. So feel free to speak. Okay, why do we do +1? Okay, so if you see here, I believe your name is Kavish. Okay. If you see here, Kavish, the IDF term here for the turns out to be 0. So and TF IDF as a whole is the term frequency into the IDF part. So if into 0 means this whole thing turns out to be 0. And if you actually see here, we have quite a bit of zeros here. So again, this leads to the sparsity problem. Let's say if we have different documents here vertically and the term frequency IDF as each of these columns here, it will lead to a lot of zeros which had the same problem, which the bag of words model faced the same problem. So that's why we add a 1 here, but I didn't add it here because I wanted you guys to think if there was any other way we could overcome this. Anyway, I believe Justin said something here. Correct, it still doesn't understand synonyms. So yeah, so it basically computes document similarity directly in the word count space, which may be slow for large vocabularies. Again, pretty straightforward. If you have large number of documents with large number of tokens, despite pre-processing, still might end up being a very large vocabulary. And yeah, this is what you just said, Justin, right now. It assumes that the counts of different words provide independent evidence of similarity, and yeah, no use of semantic similarities between words. Yeah, do you have any questions so far regarding TF-IDF? Put it on the chat box, or could unmute yourself and speak. Okay, I take that as a note. Fine. So let me quickly go over to the collab. Wait, you guys are familiar with collab, right? Yes or no? Kavish, if you're speaking, you're not audible. Okay, fine.
Oh
Perfect.
yeah, we have done it before. Yeah.
Okay. So I'll share this notebook with you guys later. This is basically an overview. You guys could refer this to understand it better. Um, so yeah. So first, 1 minute. So we import the different libraries. Don't worry too much about these libraries. You would get yourself familiarized with it as you go on. So there's pandas, there's scikit-learn, and math. So again, first sentence, second sentence, data science is the sexiest job of the 21st century, and machine learning is the key for data science. So what we first do is we split it. Guys, don't worry too much about the code. You guys, if if you're familiar with Python, then good. But if you're not, you're just getting started in college, and you would be familiar with it. And either way, we'll have a workshop on this at a later date. So just for the sake of showing you the code, I'm showing. So you guys needn't worry too much about it. So yeah, we split it according to each blank space. So this basically is for a blank space. So when it splits, we basically get a list of elements. A list of elements is yeah, like the a, and like if when we split the sentence, we'll get a list of elements which is iterable. Anyway, 1 minute. Yeah, okay. So then what we then do is we create a dictionary out of it. So dictionary, okay, how do I show it to you guys? Dictionary in Python. So this is how a dictionary would look like. This part here, basically it's a key value pair. I hope this is visible to you guys. So it's basically a key value pair. The term before the colon is your key, and the value is the term after it. So what we basically do here is that for the different tokens, we assign its corresponding frequency. We run a for loop for our two sentences here. Basically, the next step is we create a pandas data frame, so it makes it look a little bit elegant in the form of a table. So yeah, this is your bag of words representation which you learned in the last session. So now let's write the term frequency function. Again, it's basically what I just told verbally put into code. We find, we iterate over the different tokens, its corresponding frequency, and then we divide it with the total number of words. So that's what this basically does. Again, we're creating a data frame, a pandas data frame to make it look more elegant. So this is basically your term frequency part. This table which you see here, um, this is a set of stop words in English. Doesn't have uh, much use here, but I thought I'll show it anyway. So coming on to the IDF part, again, what I explained verbally, I've put it into code here. We iterate over the dictionary items. We find the total length of the number of documents, and we do the, if you see here, the math.log part. It's basically what the formula suggests, and yeah, I've added this plus one here also to ensure that we don't get a lot of zeros if it does turn out to be zero. And this is how the IDF part looks. Again, one more dictionary. So Tf Idf is basically the Tf part, which is represented by val here, and its corresponding IDF part. And yeah, so this is basically the Tf Idf data frame. You do, yeah. So now this is how we do it if we write the code from scratch. But scikit-learn is probably one of the most popular libraries out there for machine learning. A lot of work has been done to it, and they have a ready-made function which does this in one line. So basically, sklearn is the library. Um, it has this class called feature extraction, and in that comes a function called Tf Idf vectorizer. We just initialize it here, and then this function called fit transform to our two statements, and it does what? It does all of this under the hood. Basically what we did right here, all these different functions, it does it in one line, and we do the table here, which again, if you see, it's identical. Yeah, so that's for the term frequency and inverse document frequency. Again, if you have any questions, please feel free to ask. Also, am I going a little fast? You guys want me to slow down? Anyone? Is this pace all right? Okay, thank you for that, Justin. So now, um, we'll see this is basically one of the uses of term frequency TF-IDF to compute similarity between documents. So when I say documents, I mean here simple sentences, but it can be extended to what we have this image of a document as, basically like a series of sentences. But for simplicity's sake, we'll do between two sentences. So before I move on, now that you guys are familiar with TF-IDF, can you think of a way as to how we would approach this? It's not new, guys. We're familiar with it. If you want a
We'll
clue,
we'll split it into a list and then take out the higher words.
could you elaborate on that? Wait, 1 minute. Yeah, who was that? Hello. I'll give you a small hint. It's based on vector algebra, which we learned in 12th grade or 11th grade, I'm not sure. Anyway.
Yeah, 12th grade.
Okay. Can you think of how we could incorporate concepts from vector algebra to find similarity between documents? Okay, guys, when I say similarity, I mean how similar the sentences are, like semantically speaking. Can you think of a way as to how we could do
It could
that?
start with the same letters.
Not really, because see, if you think about it, there are a lot of words with the same letters but different meanings. Like
That's true. Yeah.
when you compare them, the letters they'll not obviously be identical, but a lot of common letters would be there. Do you think they convey the same meaning? Anyone? Correct. You're right, Justin. We'll take the dot product. Wait. Yeah. So what I mean by this is that if you yeah, so like basically so far we have seen as to how we basically what TF-IDF does is give you a vector representation of the particular document. Again, if you guys are not familiar with what vector representation means, it's basically an n into 1 dimensional matrix. So you won't have the row part. You'll have just different columns with different values. So basically we treat this as a vector of n dimensions. So you guys would be familiar with 3-dimensional vectors, right? 2i cap plus 3j cap plus 6k cap. So basically this is an extension of that. If you have n dimensions, we obviously don't have naming here, but the values in each of these would correspond to that value in that particular dimension. Anyway, so what we do here is we find the dot product, which is right, but we find the cos theta value between them. So let's say for the first sentence, this was our, wait, you know what, I actually do it here. Yeah, so let's say I have this graph here. My um, first document is represented like this as a vector, and my second document is represented like this. So what we found out, not we as in us, researchers found out, was that they could find the similarity between documents by computing this value theta. So that value theta obviously comes from the cos theta part from this formula you see here, dot product. Okay, I want you guys to think of, like, I represented this vector here in 2 dimensions, but I did mention that it's an n-dimensional vector. So how did I represent this n-dimensional vector here in 2 dimensions? You guys have any reason why? Okay, I think it's a little harsh to expect this answer out of you guys. So basically, in one of the ML sessions, you'd be introduced to something called dimensionality reduction. So that's basically how we reduce this n dimensions into 2 dimensions, so that we could actually visualize it. Anyway, yeah, I believe this dot product part is fine with you guys. Like, let's say consider two vectors v1 v2 v1, which basically corresponds to their Tf Idf value, and w for the other document. So v dot w is basically a normal sum of products between v1 w1 v2 w2 so on till vn wn. And the magnitude of vector, which I'm sure you all know, is the root of v1 square plus v2 square so on till v1 square. So, okay, before I move on, what do you think are the values I would get for this dot product? Like, what do you think would be the similarity score? What do you think would be the range of the similarity score? Anyone? Are you sure about that, Justin? Because, okay, I understand where that answer would be coming from, but okay, let's take another vector, which is probably like this. It's represented like this. It could be represented like that, right? There's no what restriction for that. So that time, don't you think we'd be computing this theta value, which happens to be an obtuse angle? Anyone, any answer? Perfect. Yeah, -1 to 1, but that's what it means. That's basically your range of values which cos theta can take. As simple as that. So yeah, so if it's 0, that means there's no similarity, and if the value turns out to be 1, that means they're same. So yeah, what I mean by this is that if it's 0, then the angle would be 90 degrees. Let's say there's a vector here and a vector here, so no similarity, cos 90 is 0. And if it's the same, let's say we have two vectors here overlapping. Okay, this is, consider this to be overlapping vectors, so cos 0 1, so that means they're identical and they're same. So that's when we could compute that the documents would be similar. But when we actually, yeah, so the motivation behind vector space model and cosine similarity, again, this is basically what I've just told, written in this text format. What I want you guys to know is that the answer would never turn out to be 1, unless if we are comparing the document with itself. And I think that's kind of obvious. But so when we do this document similarity problem, we set a threshold. A threshold as in, like, we could consider two documents to be similar if they're above a particular value. Say this, they're above 0.6. So if they're above 0.6, that means they're similar, and if it's less than that, then they're not similar. So the value of threshold is decided by you guys. So that's it about the document similarity. Now we would be moving on to text summarization. Again, do you think we could apply the concepts which we have learned so far for text summarization? Anyone? How we could use the things which we have learned so far for summarizing a text? Anybody? Okay, if you guys don't know, can you please type a no on the chat? Like, I don't, you guys needn't come up with like a concrete solution. Basically, what can you come up with an intuition as to how we could solve this text summarization task? Anybody? Okay, take that as a no. So yeah, introduction to text summarization, understanding the topic well. So text summarization, obviously you guys know what it means. It's the task of creating a summary of a longer piece of text. So the goal is to create a coherent summary that captures the key ideas in the text. So this is particularly useful, let's say if you're running a news agency and if you're publishing articles online, you would also have this one feature which gives you a summary and gives the viewers a glimpse of what the article is about. So there are different forms of text summarization. There's extractive summarization and there's abstractive summarization. There's query focused summarization versus query independent summarization. There's single document versus multiple document summarization. I think the last two, when I say it only, you'd be able to infer what they mean. So let me tell you what extractive and abstractive summarization is. So extractive summarization is, let's say we have this one article here. We rank the sentences which form these articles. We give them an importance value. So we'll take this top k values which are above this threshold which we set, and these sentences would is ideally considered as the important sentences. So we extract from a given article the important sentences and display it. So that's basically what extractive summarization is. Like if you see here, we have this one article here, and this model basically it infers these things which have the shade of gray over them. So that's basically what the model feels are the most important statements, which in a way conveys the whole message of the article. On the other hand, abstractive summarization, um, basically as the name suggests, it's abstract. So it doesn't draw its summary from the article, but rather comes up on with its own. So there's a lot of work that's been done on both these cases, but abstractive summarization is a very hot topic to research on because extractive summarization, it's you could you could come up with methods that's kind of easy based on Tf Idf itself, but to generate your own words to convey the meaning of an article, that's a bit tough and complex. So yeah, that's one of the hottest topics right now in the research field. Again, for those of you who use Reddit on a very regular basis, we have this Reddit summarizing bot basically does what extractive summarization does. So let me go over this. So now we would see on how to uh, do text summarization using linear algebra based on knowledge which we just which we learned in these past two sessions. Wait, before I go, do you guys have any doubts? Yes. Any doubts? You could type in on the chat box or unmute yourself. Fine. Cool. Um, so yeah, this is basically what I just talked about: extractive, abstractive, the definitions. So we will be using the linear algebra technique. Okay, the basically the Tf Idf technique to find the summary of a model. This basically this matrix which you see here, it stands for the Tf Idf which we saw earlier. So mathematical background, it basically creates a vector space out of a data set of documents, and the weight or scores give us the relevance of a term in a document. So yeah, so I'm not going to talk much about TF-IDF. I think I've spoken enough about it. So how we actually do this is that, 1 minute, let me quickly erase this. So right now we'll mainly be looking at extractive summarization, and probably in the workshop we could look into ways of abstractive summarization, because that time you would have a brief glimpse of what deep learning is all about. Maybe use those techniques for that. Anyway, so yeah, let's say we have this where's it? This article here which we need to summarize. So again, what do you think would be the first process in an NLP pipeline? Anybody? First step, typical in all NLP tasks.
Preprocessing.
Correct. So we'd basically be, um, removing the stop words. I trust you guys know what stop words are. Then we'll do lemmatizing. We'll basically reduce this entire corpus into into the terms which actually matter. So what we do here, we split it into different sentences. So for each sentence, we'll compute its TF IDF vectors. Like let's say we had a sentence, um, the class is very quiet when I entered. So okay, so we'll find the TF IDF vector for this. So basically what I mean by that is, we'll get this for, let me, 1, 2, 3, 4, 5. For these 8 terms, we'll get like values like, let's say, 0.2, 0.3, so on. So this is the TF IDF vector for a particular sentence. Okay, 1 minute. So now we will find the TF IDF vector for all the different sentences that make up the document. Do note this is done after the pre-processing steps, so we'll have this uh, huge m into n dimensional vector with all the different values. So what do you think we could do next? Any idea, like anything that's related to summation or ranking them? You guys have any idea on what we could do? Like they needn't, whatever techniques you are telling, they needn't be correct. You guys could, like think aloud. That's totally fine. Indexing. Could you elaborate on that, Suhas? When you say indexing, as in, like, you mean to say ranking them? Okay, I take it that you did mean that. So, what we do here is that we, like I said, we have this m into n dimensional vector with all these different values, zero point 0.2, zero point 0.3, so on, zero point 0.7. So for each of these, yeah, okay, this different columns would be the different terms that come in the corpus, and the rows here would correspond to the different documents. When I say different documents, different statements, I mean different sentences. So what we do here is, for a particular document, I mean sentence, we sum its Tf Idf values. All these different values, we sum them. So it'll turn out to be some value which obviously depends on the task and the corpus. So what, after doing this, we'll do it for each and every particular sentences. So, and then we will put them in one n into one dimensional vector, where n is the number of sentences in the document. So all these would be the different summation values. And what we do then is we sum these different summation values. Again, it'll turn out to be one bigger summation value. And for each of these particular values, we find its average. So yeah, so it'll basically be this summation value divided by this total summation value. So that will basically give us the average. This average of the sum of the TF-IDF scores for each particular sentence. Okay. Okay, wait. I was wrong about that. We don't find the average for these particular things, but we do find this total summation, which is basically the sum of all these values. And we basically we divide it by the length of the number of documents. Okay, what I mean by this is that, let's say we have a document which has 20 sentences, so that'll correspond to 20 different values here. And this summation we divide it by 20, so it's basically an average of the different TF-IDF scores for each sentences. So after this, we select those documents which have a higher value than this average. So that's how we rank them in a more broader sense as to how important each of them are. So if they're above this average value, we take those sentences and we deliver it to you. So that's basically a way of summarizing. Did you guys was this, did I confuse you guys, or do you want me to explain it again? Anybody? Okay, average part. Fine. Okay. Um, Justin, if you see here, this basically corresponds, this A and B are the two different sentences here, right? And this is the TF-IDF value. We have 0, 0 0.043, 0, 0, 0, and so on for the second statement. We have this particular vector, vector of values. So these A and B stands for the two sentences. So consider a document with, let's say, 10 sentences, A, B, C, D, so on. So what we do here is, for each sentence, we add its different Tf Idf values, that is 0, 0 0.043, 0, 0, 0, 0. So we do that to the second sentence, we do that to the third sentence, so on till the 15th, or how many other sentences there are in the document. Then what we do then is, sorry, yeah, we put them in this another vector of values which has this each corresponding summations, right? So after this, what we basically do is we sum these different summations. That will give us one bigger summation. The idea or the objective to do this is to basically find the average or like a threshold point. So if we find these different summations and divide it by the total number of sentences, it will basically give you the average, right? Does that make sense? Like if in statistics, that's how we compute mean, right? The Yeah. So basically, the intuition behind this is we need to have this one threshold point beyond which we'll take the different sentences. So it's basically a way of ranking them, or like, finding those statements that we feel are important, because that's what TF-IDF does best, right? It basically scales down the less relevant words and scales up the more important ones. Does that make sense? I'm gonna take that as a yes. Okay, so what do you think? Um, Sentences are of different length. You mean to say the tokens? It's basically it really wouldn't matter, right? Because again, let's say we have this. Can you see this table here? So the rows would correspond to the different documents, and this columns would be the different words or tokens that come up in the entire document. So for, let's say, let me type something here. Class was very quiet when I entered. I was surprised because I do not know why. Okay, this statement doesn't make sense, but let's say we have this different statements here, and basically after doing all the pre-processing, removing words, like removing the stop words, we'll get all these different tokens like class, quiet, entered, surprised. So this that would be represented here by the columns, right? And we have this different statements here. So if that particular token is not there in the statement, we'll give it a zero value. That's what TF-IDF does, right? Does that make sense? And then we sum these values. So it really, it really wouldn't matter. Okay, fine. So what do you think is the drawbacks, are the drawbacks for this, like this, for this entire approach which we have thought of? Anybody? Don't you, yeah, this is an example, basically this huge document here summarized into the most important statements. um, I'll share with you guys. You guys could actually go through this and see if the summary is actually right or not. So yeah, so this algorithm to generate a summary based on TF-IDF code has been through iterations of modifications over the years. So one thing which is rather surprising is that it has been observed that keeping stop words instead of removing them, which is the usual norm, and taking in the different nouns and parts of speech terms sometimes leads to better summaries. So there's no real proof behind this. It's just an empirical observation. So the TF-IDF weighting methods, it basically accounts for context through n-grams, and so it basically retains the structure of the summary without giving much attention to the semantics behind it. So that's basically one of the drawbacks of um, summarization based on TF IDF. Okay, you guys know what n-grams mean, right? Yes or no? Okay, you don't know what. Okay, sorry about that. Uh, n-grams. Okay. Okay, never mind. You know what? Okay, so I hope this is visible. So let's say this is a big data artificial intelligence book, AI book. So a unigram is when you take these tokens individually, which is this is big and so on. A bigram is when you take these tokens two at a time. This is big data and so on. And a trigram, I mean, you guys could make it out. So an n-gram is basically whatever value of n you give, you take n tokens at a time and you put them. So why we do this is because like if you think about it, when you're actually writing, let's say a particular summary of a given document, certain words obviously come after each other. Like you can't have words as per your choice. Like in order to for them to mean semantically to be semantically correct, certain words have to follow certain words. Like so I mean I guess you understand what I mean by this. So when we do this n-gram concept along with TF-IDF, basically it's accounting for the context, right? Did you guys do you guys understand by what I meant by this? Okay, perfect. So yeah, again I'll just say it out. TF-IDF summarization, it accounts for the context but not for the meanings. Again, what I mean by this is there can be different synonyms which the TF-IDF model cannot understand, but it captures the context well because of this n-gram approach. So I would have shown you guys the code for the same, but we have an workshop anyway dedicated for this alone. So there we'd explore more on this. So yeah, that brings to the end of okay. Yeah, practical advice for summarization in case if if our sessions did inspire you and you want to delve more into NLP and its different research, always remember for summarizing, they're evaluated using a common data set of reference summaries created by humans, us of course, called rogue. Now don't ask me what rogue is, it's one abbreviation, even I forgot. And most summarization algorithms are sensitive to the size of the text given as input. For example, text rank runs in polynomial time, so it can easily take up a lot of computing time to generate summaries. So what I mean by the size of the text given as input, uh, when you come when you come to second year, you would be introduced to terms like time complexity and the big O notation. So it basically tells you it's a way of comparing different time complexities based on a given input. Like you can have let's say big O of n. So what? Wait, you know what? So big O of n is basically saying it linearly depends on the input n. So the time taken depends linearly. So if you have something like O of n cube depends on the cube of the input. So intuitively, as the size of the n increases, the time increases, so the computational expense increases. So this is something which we try to avoid for obvious reasons. So I'll again, do you have any questions so far? Anything? Okay, I'll take that as a no. Um, I'll share this PPT with you guys. There's some external reading material you could read into these papers which inspired these different algorithms. There's also a book called Practical Natural Language Processing, which I'll share it with you guys. It's, I feel, one of the best introductory books. It covers almost all aspects of NLP, so you guys could always look into that. But please don't, put it on the internet or something, because this is not a legal book which I've downloaded from. It's basically a torrent. So yeah, thank you, and yeah, feel free to get back to us on the Discord server if you have any doubts. Anyone, any doubts? Oh yeah, recorded this session also, so